Hi everybody. In this lecture, I'm going to begin Chapter 4 in Matter and Interactions, which is entitled Contact Interactions. And in this lecture, we're going to specifically start with the ball spring model of a solid, which is covered in sections 1 through 4 of that chapter. So, what we can do is, in a solid material, we can model the atoms as little spheres or balls, and then the bonds that connect those atoms together as little springs. Now, this is a really common view, and it's used to describe a lot of everyday behavior. For example, if you've taken modern physics, you might have heard about Max Planck's model of a solid, which was very similar to this one and used to explain black body radiation. And also, there's the Einstein-Debye model of a solid, and that's an adaptation of this model in Planck's model. Now, this is a great model, actually. It works really well to explain a lot of phenomena and provides a good conceptual foundation. And the reason it works is because if you think about what's going on in an atom, in a solid material, if you displace one of those atoms away from the equilibrium position, right? Like if you try to shove the atoms together or pull them apart, say you're applying a compressive or tensile load, then those atoms are going to resist that change and then try to spring back to their equilibrium position. But they will move about those equilibrium positions. Now, in a solid at room temperature, it's also understood that atoms are going to be wiggling about those equilibrium positions. And so it's true that the atom will sit there and vibrate with respect to its equilibrium position. And that's much like a mass on a spring. Now, you might think to yourself, well, there's no way that the potential energy or the force for a bond is the same as the force for a mass on a spring. And that's true. But let's take a look at their potential energy functions, which are shown here. On the left, this is the potential energy for a simple harmonic oscillator, which, if you might remember, is 1/2 kx squared, where k is the spring constant of your spring, and x is the displacement of that mass on the spring from its equilibrium point. And so it's got this, characteristic parabolic shape here. Now, on the right is the Leonard-Jones model of the potential energy for a bond. Now, you can see that it is different. Here on the left-hand side, here we've plotted the potential energy versus the separation in between neighboring atoms, okay? And so as you go to r equals 0, of course you're going to have that hard wall repulsion, and so your potential energy function is going to blow up as r approaches 0, as it should, right? And then on the right-hand side, as you pull it apart, you'll have this kind of long tail to it. But if you look in the region about the minimum potential energy, which is the equilibrium separation in between the two atoms in the solid, then you can see that it's got that same kind of parabolic shape that the potential energy for a simple harmonic oscillator is. And so it's actually pretty well fit by a parabolic function down here in the minimum and for low separations, low deviations from the equilibrium separation. And so that's why it works pretty well for modeling a lot of phenomena. Now, we can use this model to explain a lot of different everyday forces, okay? And we will do that throughout this chapter. For example, in the following lectures, we're going to talk a lot about tension. Remember that tension is a pulling force that a string, chain, rope, something like that exerts on an object tied to it. And that when you suspend a stationary object from a string or a chain or a rope, if you assume no other forces, then what's happening here on planet Earth is that the mass has some weight that pulls it downward, and assuming that the mass isn't accelerating in any direction, the only other force that's acting on it is the tension in the rope that's acting upward, which is balanced by the weight acting down. And so the tension force will equal the weight down in its magnitude. Now, what will happen is if you increase the weight that you've tied to it, the tension is going to increase as the load increases until the string eventually will break. And scientists, of course, notice that metal wires will stretch before they break, right? And so one of the causes for that is if you envision what's going on in a chain, rope, or string or something like that, you could think of it as a solid material, right? Now, this is a very simplified, tiny little string here, obviously, because we've just got a one atom wide chain, and real strings are, of course, going to be many, many atoms wide. But even in this simplified picture, you can see here that what would happen is, let's say that you've got this hypothetical string with this, really small width of chain, and the atoms in the chain are attached to one another by these bonds, which are modeled as these little springs. And so what happens is, when these are placed under a load, of course, it's going to stretch, right? It's going to stretch your springs. We've seen this in demos in class with masses on springs. And so the interatomic bonds in a wire are actually going to stretch too if you hang a heavy mass from them. And the stretch here is really exaggerated. Now, this isn't a bad model, okay? Bonds really do stretch like springs when they're pulled. In a real wire, of course, the thickness is greater than an atom, but if you use this model in a ceramic or something like a metal at very low stress or force applied, it's not a bad mental picture. Now, I'd like to say that atoms really are kind of little balls. This is a scanning tunneling microscope image of a platinum 111 surface. And the scale here is that these little atoms are about 0.28 nanometers apart. So this is an image captured by a microscope, which can visualize things at this length scale. And you can see here that your platinum atoms really do look like little spheres. Now, you can resolve more than that if you chill down your surface, your metal surface. There have been some scanning tunneling microscope images taken where they actually imaged the orbitals of the electrons within the atom, and that's pretty amazing. But the truth is that at room temperature, these things are jiggling around a little bit too much, and so this kind of stuff gets smeared out. And what you really see are these little balls. And so basically, the model is very good in envisioning an atom like a little ball. It's just a very tiny little ball. So there you go. So I hope I've at least motivated and convinced you that the ball spring model is not a bad model for a lot of different applications. Now, what is one of the first things that we're going to do? If we're going to develop this model, we need to figure out many things about our little bond springs, right? We need to figure out their spring constants, okay? And we also need to figure out their equilibrium separations, okay? So we need, remember, Hooke's law says that the magnitude of the force is k delta x, where k is the spring constant, and delta x is that displacement from equilibrium. And so we would need to be able to quantify those things in some way. So first of all, let's calculate our equilibrium bond lengths, and that'll help us know how much our bonds, our little springs, are being stretched. Now, how are we going to go about this? Well, if we know the density of a material, which is something that you can look up in a table or measure experimentally, and you also have the periodic table handy, then it's not too bad to calculate a bond length. For example, you can look up the density of copper. It's about 8.94 grams per cubic centimeter, okay? Now, using that information and the information that you can read off the periodic table, then you can do basically a unit conversion of the mass density into a number density, and from a number density into a bond length. And we're going to go through that calculation in just a second. So first, let me tell you a couple things about the periodic table entries that you're going to have to know. So if you stare at a periodic table, you see a couple of numbers. So of course, here's Cu for copper, that's the symbol. 29 up here is the number of protons in the nucleus, and of course that's also the same as the number of electrons in a neutral atom of copper. And then this mass down here is the atomic mass displayed in atomic mass units. It's the mass, the average mass of a copper atom in atomic mass units. So a copper atom has 63.55 roughly atomic mass units per atom, and you can just read that right off the periodic table. Now, a little bit more information about our periodic table. One atomic mass unit is 1.66 times 10 to the minus 27 kilograms. That's the conversion. The atomic mass unit is a really handy unit for giving information about the mass of an atom, okay? But for real-life objects, of course, 10 to the minus 27 kilograms is a really tiny number. Now, if you convert that to grams, that's 1.66 times 10 to the minus 24 grams. Now, I'd like to point out here that this mass is actually a really special number in another way. If you take the inverse of 1.66 times 10 to the minus 24 grams, you'll see a familiar number, 6.022 times 10 to the 23rd. And that's Avogadro's number, which is the number of constituents in 1 mole of a substance. That's actually by design. So we chose our units here. We picked Avogadro's number such that 12 grams of carbon-12 resulted in a mole of carbon atoms, which is 6.022 times 10 to the 23rd carbon atoms. And we did that so that you can read the number of grams in 1 mole of a substance right off the periodic table. And it would also be the mass in atomic mass units of 1 atom. Okay? So for copper, it's 63.55 atomic mass units, or 63.55 grams of copper in 1 mole of copper, 63.55 grams per mole. So what we can do is to, let's make this a little bigger, this is teeny. There we go. What we can do is we can do a little calculation here for our unit conversion now that we're armed with this knowledge. The density of copper, as I said, is 8.94 grams per centimeters cubed. And now I'm going to take that number and convert it, right? So what I've done here is I'm converting from grams per cubic centimeter to atoms per meter cubed. To convert from grams to atoms, first I have to use the molar mass of copper. So I would divide by 63.55 grams per mole, as you can see here. Now I've got moles per cubic centimeter, so I need to convert from moles to atoms. So to do that, I multiply by Avogadro's number, 6.022 times 10 to the 23rd atoms per mole. Now, I'd really prefer to have it in meters cubed for simplicity, okay? And so I need to multiply times the conversion for centimeters to meters cubed. Remember that if you're converting a unit, you cube the conversion and not just the unit. So here I've got 100 centimeters cubed, so I'm multiplying by 100 cubed. That results in 8.47 times 10 to the 28 atoms per cubic meter. So I've just converted from a mass density to a number density. Now, if you take the inverse of that number density, it'll give you the volume occupied by 1 atom of copper, right? Because it's atoms per meter cubed. So if you invert that, it would be meters cubed per atom. So we can then use that and solve for the radius, right? So 1 over 8.47 times 10 to the 28 atoms per cubic meter is 1.18 times 10 to the minus 29 meters cubed. That's the volume occupied by 1 atom of copper in the lattice. And then I can set that equal to 4/3 pi r cubed, which is the volume of the sphere, and solve for the radius. When I do that, I get r is equal to 0.14 nanometers. Now, twice the radius would be the distance between neighboring copper atoms in the lattice, and that would be our bond length. So 2 times the radius is 0.28 nanometers, and that's our estimate here using this simple model for the distance between neighboring copper atoms. Now, this assumption was predicated on the idea that I've got just a very simple cubic lattice, and that's not quite true, right? Copper actually occupies a face-centered cubic lattice, and so the real neighbor-to-neighbor distance would be 0.254 nanometers. But you can see that even without knowing any of that, I've gotten actually a pretty good estimate. So our simple little model isn't a bad model. Now, you might have heard of a unit called the angstrom, and if not, welcome. Okay, here you are. The angstrom gets used sometimes because it's actually the length of a lot of different bonds on the order of that. And so the angstrom is 1/10 of a nanometer, or 1 times 10 to the minus 10 meters, and that's an angstrom. And the symbol for it is this A with this little circle over the top. So if you see that symbol, now you know what it means. All right, one more thing. Note that the bond length for copper will vary depending on what it's bonded to. This little simple calculation that I took you through was just for pure copper, but if you had some compound like copper sulfate or something like that, then you would expect the bond lengths to be different and the densities to be different. Okay, I hope you understood that and enjoyed it. If you have any questions, let me know, and as always, I'll see you in class.